Hi, my name is Owen Seibert. I'm studying mechanical engineering here at the University of Colorado Boulder. I'm currently in my final year. This semester, I had the opportunity to work with Dr. Keith Regner on an independent study to create electronic ignition for my 1976 Honda MR175 two-stroke dirt bike. This independent study allowed me to get engineering experience that I wouldn't otherwise have had in a classroom. It allowed me to mix my passion for engines, cars, and bikes with my engineering knowledge and interests in circuits and electronics. Before I go further about the details of this project, I would like to take some time to thank my faculty advisor, Dr. Keith Regner. He took this independent study on as extra in addition to his workload and teaching schedule this semester. So thank you for the time and energy you put forth into this project and meeting weekly. I would also like to thank the ITLL engineering staff for their help and advice in circuits. Ignition systems and engines allow for gasoline to be burned and converted into useful rotational mechanical energy. Before the widespread use of consumer electronics, ignition used to be controlled mechanically. Now this is a spark plug. It bolts directly to your cylinder, exposing itself to the air-fuel mixture that mixes inside the engine cylinder. This thing takes 20,000 volts to create a spark across this small gap. To give the spark plug the 20,000 volts required to make a spark, a coil is used. This thing is a transformer that is charged and transforms 6 volts DC to 20,000 volts DC. It is connected to ground, the spark plug terminal, as well as the positive 6 volt supply of power. For the spark to occur, the charging voltage of 6 volts has to be interrupted. This is done by a set of mechanical points, which open based off a cam lobe positioned on the flywheel. Here is the flywheel that goes on the engine of the dirt bike. On it is an array of 6 magnets that uses Faraday's law of magnetic induction to induce a voltage useful to charge the coil. Also on this flywheel is a cam lobe. The lobe opens the points at the same time every single revolution, meaning the timing is fixed at a specified 20.5 degrees before top dead center. Today, cars use electronic ignition to control the spark plug. Electronic ignitions allows for greater control of the combustion process, leading to more power and less emissions. With electronic ignition, there are sensors on the crankshaft to detect what position it's in. This is analogous to the cam lobe on the dirt bike's flywheel. I wondered if I could use similar sensors on my dirt bike to create electronic ignition. So I did. I used a Hall effect sensor, which detects the presence of a southward-facing magnetic field, in addition to using neodymium magnets on the flywheel to detect what position the crankshaft was in. We use a sensor and a magnet mounted to the flywheel to calculate rotational velocity of the flywheel. Then, by using kinematics equations from physics, we're able to predict the amount of time it takes for the flywheel to pass to the optimal ignition position. This calculation is done in a microcontroller called an Arduino. The Arduino was programmed using C++ to interface with our Hall effect sensor as well as the engine's already existing electrical harness. In the code, we were able to program these equations that calculate and predict the amount of time we needed to wait for spark to happen. In our developed electronic ignition system, we elected to use a 6-volt battery to charge and generate the spark. This differs from the stock mechanical system, which uses the electricity from the alternator to generate spark. We decided to go with this setup as it gave us more control over the variables that may affect the outcome and performance of our circuit. Something else we had to consider with our Arduino-based electronic ignition system is that the Arduino can't handle the amount of electricity needed to generate the spark. Transistors allow you to control a large amount of amps with a small amount of amps. The Arduino can't handle the amount of electricity used for a spark, so rather we used a very small amount of electricity to control the charging circuit for the spark plug. So this is the actual wiring diagram we used in our circuit. Here, the Arduino controls the transistors, more specifically the tip 31, that allows electricity to flow from the battery to charge the coil. Then the Arduino stops charging the coil, releasing a spark at the spark plug. You can also see our Hall effect sensors connected to a digital input pin, as well as power and ground. Next is the Arduino's code. Here, we initialize all of our input pins and output pins, as well as initialize our timer that indirectly allows us to calculate flywheel velocity. The next part of the code is where we measure how long it took for the magnet to overpass the sensor. The amount of time we need to delay before spark is linearly proportional to the amount of time the magnet took to pass the flywheel. We broke up the delay time into 10 separate blocks. Since we were measuring microseconds, the variable storing that information would have overflowed if we hadn't separated into 10 separate blocks, causing weird issues and calculated negative delay times, which just doesn't make sense. During testing, we decided to make a mock flywheel with 2 magnets on it, both facing south towards the sensor. This proved that we were able to delay and spark a spark plug represented by the LED. This allowed us to verify that our Hall effect sensor was working with our Arduino circuit to simulate a spark with an LED. After weeks of testing and verifying that our soldered circuit worked in the lab, we felt comfortable to start moving the setup to the actual engine. This is when we made a more robust sensor housing to integrate to the bike using an old coolant sensor as well as epoxy securing it in place. The Hall effect sensor is in this coolant sensor housing and potted with epoxy. We chose to put it on this side because the flywheel also exists on this side of the engine behind this cover. So here's the Honda MR175 with the project electronic ignition on it. It's currently ratchet strapped to the gas tank. Dr. Regner also helped with making the circuit a lot more robust as well, as you can see. Behind it is the 6-volt battery running the ignition system. It also powers our Arduino and circuit. The Arduino circuit breadboard takes in power from the battery, takes in information from the Hall effect sensor down here, relays that information back up to the Arduino, where it then outputs a signal that goes to the coil tucked underneath the gas tank that tells the spark plug to spark.
What do you want to put it to?
I want to try like 25.
Baseline.
Sure. There you can see the project worked. We were able to successfully create electronic ignition, adapting to this 1976 Honda MR175. The clip that you just saw of it running, the bike started off of just one kickstart. Then Dr. Regner and I tow-started it around my neighborhood for about 20 minutes before it stopped sparking. Another thing I suspect was an issue during testing was the fact that the engine had laid unrunning for about 6 months. It took a lot of time for Dr. Regner and I to dial in the carburetor to a setting we thought was appropriate for the bike to run. But by that point, the battery powering the circuit and spark was low enough that it wouldn't be able to generate a strong enough spark to ignite the air-fuel mixture. If I were to do this again, I would adapt the engine's alternator circuit with our electronic ignition circuit by using a rectifier, rectifying the alternating current signal from 6 volts AC to 6 volts DC. This would mean while the bike's engine is spinning, power is being generated. Another recommendation I have for the future is moving the magnet on the flywheel closer to the ignition position. This way, you can assume constant acceleration of the flywheel, or rather deceleration of flywheel, in the engine's cycle. I suspect that the piston slows down on its way up while it's compressing the air-fuel mixture, meaning that the kinematics equation that we used doesn't properly account for the deceleration, meaning more time is needed to delay before spark. I plan on incorporating these learned lessons back into this project to hopefully make a bike that does completely run on electronic ignition. This project was a highlight of my semester, as it allowed me to utilize a lot of skills I learned in my degree thus far to make an electromechanical system that worked on one of my projects and hobbies. It was also nice to work with and get to know Dr. Keith Regner better. He's got really cool stories about adventuring in his Volkswagen van again with his cat, and also enjoys tinkering and crafting random things on the weekends. So, again, thank you, Keith. I really appreciate the time and effort you put into this project, even working on the weekends. Without you and your support, I would have never had this experience. Again, I would like to thank the ITLL engineers and staff for helping me troubleshoot and problem solve the circuit for this project. As a whole, I feel proud of the work I've done this semester and feel that the time I put into this project was well worth it. I'm looking forward to getting this bike fully functional and running again, to rip again in Utah like you see here.